Hey there, this is Raimu. This is part 12 of my Introduction to Rust series, Learning One Step at a Time. Today we're going to be talking about boxing and trait objects. But before I get into that, I need to explain a little bit more about the different kinds of memory that we deal with in Rust and in other programming languages, based off the traditional memory model of computers. So going back to one of our previous parts, part 3. So if you look back here at part 3, where we first introduced values, the memory which is going to store these values is on what's called the stack. It has to do with temporary values that exist only as long as functions are called. So there are 3 other kinds of storage for variables that we're going to introduce in this video. Let's go to a project that I've prepared to demonstrate this. Now, if values that are introduced with the let keyword are on the stack and they're temporary, only exist as long as the function is called, then how do we make more permanent values? In fact, how do we make values that don't change at all, and so maybe they don't even need to be put into the memory at all? The answer to that are global variables and constants. Constants are the easiest to describe. They can be declared anywhere. They can be declared outside of a function or inside of a function. They're basically binding names to values that never change, and so that the compiler doesn't even need to have memory allocated for them anywhere. They can just be baked into the program. So const is the keyword that's used instead of let. In most cases, when you declare constants outside of a function, you actually do need to annotate the type directly, because the type needs to be known outside of evaluating any particular function. Now, what if you wanted a variable stored in memory independent of functions that can be changed over time? That's known as a global variable. Rust does allow you to have global variables, but they're very limited because of how unsafe it generally is to manipulate global variables. You use the static keyword instead of let or const in the case of making a global variable, and you generally declare it outside of any function, just like a constant. What makes it different from a constant is that it actually has storage in memory somewhere. And so you can mark it as mutable if you want to change it. Now, a couple limitations about global variables. Because of how inherently unsafe they are to manipulate, you could have different parts of your program accessing the same global variable at the same time, getting unpredictable results. There are 2 rules about global variables in general. One is that you can only construct them with constant values or values that are generated from so-called constant functions. So for example, string new is a constant function. It has const in the keyword. If we instead tried to use from, which is not a constant function, we would see that we get an error here. Calls in statics are limited to constant functions. So generally what it's saying is the compiler can only initialize a global variable if the value is known at compile time. Either it's a constant or it's the value generated from a function which is itself constant. The second way global variables are limited is in that their access is inherently unsafe. And so down here in the main function here where I'm actually initializing and using this global variable, I have to wrap the whole block of code and put the unsafe keyword in there. This is the first time we've seen this. Generally, you want to avoid using this keyword. What it does is it kind of takes the safety bolts off of the code, lets you run things which are not normally safe to do or could lead to undefined behavior. Now, the whole explanation of why global variables are unsafe to access could be itself a video, so just suffice to say that global variables are very restricted in how you can use them. It's inherently unsafe to access them, so you'll need to have the unsafe keyword in front of them. One general recommendation, if you really do need to have a global variable, is to actually have a stack variable declared in the main function, and then let it be borrowed or copied throughout your code. So I've covered variables on the stack, which are temporary, and then variables which are more permanent, like constants and global variables. What's this 4th kind of variable? The answer is it's a heap variable. To explain what the heap is, let me first introduce a problem with the stack. As you see here in my example program, I am calling a function which is generating some huge type, an array of 10 million numbers. Seems logically correct. We declare an array of 10 million numbers, and we iterate through them and set them all to be the index of the number times 2, and we return that, and we're just going to print out the first 5 of them, right? So let's just run this and see. It should work, right? Uh-oh, thread main has overflowed its stack. Now, why did this happen? In most operating systems and programming environments, the amount of memory allocated to the stack area, or temporary variables, is rather limited. It's generally safe to have variables which are small or medium size, but when you start to get to huge objects like in the megabytes, you run the risk of running out of that stack memory. So what do we do if we want to have such a huge array for some reason? Maybe we're doing some kind of complex mathematical analysis and we really need an array that can store 10 million numbers. The answer to this is the heap. The heap, think of as a general purpose store of memory where you can allocate pieces of it at any time. They're not temporary, so they can remain allocated as long as your program is running, or less time than that. You can free them and return them back to the heap. So to allocate values on this heap, Rust provides a facility called box. And I have here an alternative to generate numbers called generate numbers on the heap to illustrate. As you can see, the type is a little different. We still have our sum huge type, but we've put it into this generic thing called the box. First, let me demonstrate how this gets us out of our problem of Stack Overflow. If instead of calling generate numbers, we say generate numbers on the heap and run this, the program works, although you could tell there was a little bit of a pause there. It takes a while to fill in 10 million numbers. Going into the details of how we generate this box in the heap, I have to be a little bit careful in explaining this because there are still little rough edges around box in Rust that potentially will be made easier in the future. But suffice to say, there are two steps in making our allocation and filling it in. First, we need to allocate the memory that the 10 million numbers will reside in. And then once we have that allocation made, we're going to want to manipulate that and return it. So as you can see, the rest of the code is pretty much the same. And as you might be able to figure out, box is really providing an almost transparent layer for us, giving us a value that we can manipulate as if it was the array, but placing it in a different region of memory on the heap. You can think of box as a sort of pointer. I know we haven't talked about pointers too much, but it's a value which really just stores the address in memory of where the real object is. So the size of numbers box itself is very small. It's only the size of the address of the object. The actual storage of the object is on the heap. Therefore, when we return our box, we're not having to copy 10 million numbers on the stack to the calling function or having to allocate that space on the stack in the first place. We're just returning a very small pointer value. Box is sort of like in C++, you have what's called a smart pointer, like unique pointer, where it handles deallocation by freeing that memory and returning it to the heap when the value is out of scope. So for example, at the end of our main function down here, when numbers is no longer needed at the end of the main function, it would be automatically freed. Now, how we get the memory allocated in the first place is a little bit tricky in Rust. So although I'm going to show you what the allocate numbers function looks like, I'm not going to explain it in too much detail because this is really only something you need to handle if you're making your own types that are really huge. Basically, there are two steps to the process and they're both unsafe. The first step is to use an allocator. There's a global allocator, there's an alloc function, and it works with this type called the layout. Basically, we're saying we want to allocate memory, and that memory will have the shape of the huge type that we have declared here. And what we get back from alloc is a raw pointer. Now, we haven't seen this asterisk, this star pointer yet. It's just like it is in C and C++. It's literally a pointer or an address into some other region of memory. In this case, it's the heap. Now, why it's unsafe to call alloc directly like this? It's because it's not guaranteed that this layout has a non-zero size. I could go into more details about that, but I recommend you read the manual for that kind of level of detail. The second thing we're doing here that's unsafe is we're taking that pointer and attaching it to a box. Now, working with pointers in general can be a little bit unsafe in Rust because, as you might expect, what if we called box from raw twice and made two boxes that were managing the same pointer? End up with what's called a double deallocation or a double free, in that you've somehow attached the same pointer to two boxes, and so it'll actually get freed twice at the end. So once again, putting these two lines inside of a block marked unsafe is letting Rust know that we take on responsibility over this code, and we guarantee that it's going to operate correctly. And if it doesn't, it's not Rust's compiler's fault, it's ours. So putting together all that we've gone through so far, just remember there are 4 areas of memory in general in Rust and other programming languages you'll deal with. That's constants, global variables, values on the heap, and values on the stack. In Rust, constants are declared with the const keyword. Global variables are using the static keyword outside of functions. Stack variables are with let, and heap variables are with box. So to give you a different perspective on box and how you might find it useful, let's talk about a structure called binary tree. You may or may not be familiar with this. If not, that's fine. So like it says in Wikipedia, binary tree is a kind of data structure in which we're going to organize information that is related to each other. So in general, you have a root or a start node, and then it can have child nodes left and right, and it's recursive. So each child node can itself have a child node, and when you get to the leaf nodes, they don't have any children. So structures like this are useful for organizing information when you're doing sorting and other things like that. How would we represent a structure like this in Rust? So if we try to define such a structure, let's think of it in terms of any individual node, because when you think about it, if we had a structure that represents the root of this tree and then recursively contains its children, then this node could just be the value that's at that node. So in this example, it was a 2. So we'll just pick a value like some number, and then we'll have our left child, which is an optional node, and then our right, which is an optional node, right? I'm picking option because at any point within this data structure, you may or may not have left or right child. So for example, this 9 has a left child 4, but the 11 at the bottom doesn't have any children, but the 2 at the root has both left and right children. Now we're going to run into a problem right away when we define the structure. Rust is going to tell us that this structure has infinite size. And when you think about it, it does. Because what is option? Option is an enumerated type that has 2 variants, and as we covered before, the size of an enumerated type is the size of the largest variant. So in this case, that would be sum, because with none we have no associated data, but with sum we have that value t. Now unfortunately, that value t in our case is itself a node. Rust has to cover the worst case scenario where every node has both children, and those children have their own children, and those children have their own children, and so on ad infinitum. So the way we solve this in Rust, like in other programming languages, is to introduce indirection, in which our left and right nodes are stored in an area of memory not directly contained in the parent, but referred to it through a pointer. And as we just introduced, box is a kind of pointer. So in the case of this left and right, we can, instead of saying node, we can say box node. That solves our problem. So how would we construct such a node? Let's say, for example, our root node is a node, and let's give it, just like we had in our example here, 2 for our root node. And for left and right, let's just start off with none. Let's make this mutable so that we can change it. So then how would we fill in that left node? For example, here we wanted to have a 7 to the left of 2. We could say root.left is a node, value is 7, and just copying the rest of this. So there's 2 problems here. How do we put it into an option and a box? Let's solve them one at a time. To make it into a box, we use box's new function. Now I didn't use this in the previous example because there is one problem with box new, is that the value that you are going to give to box new is actually on the stack, and box new then copies it to the heap. So if you're creating a box that has some huge data structure in it, box new isn't going to solve the problem of overflowing the stack. For values that are small like this, though, it's nice and convenient. So the other problem is, of course, how do we wrap it into an option? And that's merely just giving this to sum. So not to construct the entire tree, but let's go and put that 6 node in there as a right child of 7. So we'll just fill it in the same way we filled in root.left. We'll put it in here for right. Put a 6 there. Now if we wanted to, we could even not make root mutable at all, but simply take this entire thing and put it in place of this left here. And just for fun, let's make a recursive function which prints out our binary tree. Let's make it a method of node. Function display, borrow self, and we'll just say print line self value. And we'll say if let sum left equals self left, then left dot display. And we'll do the same thing for the right. And let's also print something that tells us which path we're taking, either left or right, as we're going through this. And finally, at the end, let's say up, just so that we can see the paths that we're navigating here. Remember, we need to borrow these since we're not moving out of it. At the bottom, let's just run root.display. And take a look at that. We can see that it navigated our structure. It hit the root node 2, went left, printed 7, then went down to the right, printed 6, and then all the way back up the tree. So far we talked about how box is really useful for holding on to very large objects that won't fit on the stack, and also how we can use it to make interesting data structures that require indirection. So let's talk about a third use for box, which is useful for what's called dynamic dispatch, which is used quite a bit in object-oriented programming. Let's start over with a new main. Let's define a couple types and then a trait that kind of binds them together. And just for fun, let's call one of them cat and the other one dog. And what they share in common is a trait called animal. So let's say that both cat and dog have to implement some function called speak that borrows self, and then we need to implement how cat and dog speak. So implementing animal for cat, let's have the cat print out meow. Similarly for dog, let's just copy that, and we'll have the dog say woof. And in our main program, let's make a cat and a dog, and let's have them both speak. You can probably imagine what this will do when I run it. The cat says meow, dog says woof. But let's say we want to take our cat and dog and put them together in a group, pass them to a function, and have that function iterate through and have them both speak. So we would want some kind of function. Let's call it work with animals. And let's say we want to handle animals as some kind of slice that works with animals, and keep in mind that this isn't valid Rust syntax yet, but conceptually, we want to do something like this. For animal and animals, animals speak. So instead of having the cat and dog speak correctly, we would do something like let animals equal some vector, and then animals push cat, and before I forget, let me make that mutable. Animals push dog, so that we can call work for animals and let it borrow animals. Now when we mouse over this arrow, we're going to get a spoiler in that it's going to tell us to use the dyn keyword. The reason is that traits are not in themselves types in Rust. Unlike in C++ where you might declare a base class animal and then pass a pointer or a list of those pointers to your base class to a function, we can't do that directly in Rust. But Rust does provide a mechanism for linking traits to objects, and that's called the trait object. Simply put, if we put dyn keyword in front and then we box that, now work with animals is correctly defined. Now let me explain the two things that I did here. First of all, we need to say that the type of each animal is handled through a trait object, and dyn or dyn is the prefix that you use along with the trait name to declare a trait object. Think of a trait object as representing some object that implements the trait. Now we don't know which kind of object it is, therefore we don't know the size of it, so we need, again, some form of indirection, and here's where box comes to the rescue. So box works with trait objects by holding on to two pieces of information. A pointer to the actual animal, the cat or the dog in this case, and also a pointer to a what they call a virtual table or a V table or a dynamic dispatch table, basically a table of all of the methods that apply to that particular animal. So either the cat or the dog implementation of animal and all of its methods. So to make this work, of course, we're going to need to box our cat and dog to make them into trait objects. And we're going to have to give Rust a little bit of help telling it the actual type of this, which is a boxed animal vector. Dyn in front of animal, run our program, and it works again. So one important thing to point out that happens when you represent something as a trait object and box it. Once our cat and dog are boxed as trait objects and passed into work with animals, this work with animals function no longer knows that they were cats and dogs. They only know them through the animal trait objects. One might say that the type cat and the type dog have, in this sense, been erased, as in the code no longer knows the original types. If, say, we had special functions for our cats, in order to get back to them, we would need some way to figure out which animals were cats in the first place, and that's the subject of a different video. All this function really knows is where these animals are, and it has a table of methods that it can call for them that are essentially the implementations of the animal trait. Another place where box trait object is really useful is when you're dealing with many different kinds of error object types, Like we covered in the last video, we could declare our own error type. Standard library has their own error type. If you have a lot of error types that you're having to handle together and you need to treat them under a single umbrella, one way to do that would be to use result with a box dyn error. In this case, we don't have any errors. Let me just import standard error. But you might run into this in Rust where if you have many different possible types of error, it can be convenient to bundle them all together under this umbrella of a boxed error trait object, so that when you return it, the caller can deal with these different kinds of error types without having to know all of them. So in summary, we learned about boxing or moving values onto the heap in Rust, and we also covered trait objects and how we can so-called erase the types of objects and deal with them indirectly through the implementations of their traits. In the next video, we're going to get into what's called reference counting and interior mutability. So I hope you'll stick with the series, and thanks for watching.